Hello everyone, I am Anurag Roy, a PhD student at the Indian Institute of Technology, Kharagpur, India. Today, I'll be presenting our CVPR 2024 paper titled Convolutional Prompting Meets Language Models for Continual Learning. Inspired by how human beings learn, a continual learning refers to a learning paradigm where a model can learn a new task without forgetting the previous task's knowledge. For example, a model capable of continual learning, like the one shown in the picture, should not forget how to classify cats and dogs while learning cars versus planes classification. Now, recent prompt tuning approaches have demonstrated the ability to adapt to emerging or challenging concepts using learnable prompts. However, the question remains, how can this approach be implemented in a continual learning setup? While there have been a few works in this direction, including L2P, dual prompt, and coda prompt, however, these approaches lack an effective mechanism for inter-task knowledge sharing, resulting in suboptimal performance. Additionally, they introduce a fixed number of prompts per task, regardless of the task similarity to previous ones. This not only increases the number of parameters, but also leads to overfitting in fine-grained datasets where the tasks are highly similar. Tackling these issues, in our work, we proposed a novel convolutional prompting approach for continual learning. We call our approach conv-prompt. In conv-prompt, the task-specific prompts are generated by applying convolution over the layer-wise task-shared embeddings. For each new incoming task, the number of new convolutional kernels or prompt generators is decided by task similarity calculated using language models. Now let's take a closer look into our approach. We apply prompts to the keys and values of the pre-trained transformers, which are highlighted in gray. For that, we pass the CLS embeddings from the previous layer through the projection network and match them with prompt keys to get the similarity values. These similarity values will be used to weigh the prompt components, which we'll be describing in a moment. Now we apply the prompt generators Gs over the layer-wise task shared embeddings AC to get the prompt components PCs. A weighted summation of these prompt components using the similarity values as weights is performed to get the prompts PK and PV. Now the next question is how to determine the number of prompt generators to be added per new task. For that, we get the visual attributes of the classes by prompting GPT-3. We get the BERT embeddings of these attributes and store them in a pool for all seen tasks. Now for every new incoming task, we compute the cosine similarity between the attribute embeddings of the task and those present in the existing pool of tasks. Here is an example of to show how the task similarity is calculated. The first task contains the classes lorikeet, hummingbird, and toucan. The second task contains the classes hermit crab, flamingo, and American egret. Here are the attributes, and the dotted lines indicate the cosine similarity values of the most similar attributes between the tasks. We calculate the task similarities as the average of these cosine similarity values. Now, the number of prompt generators required is calculated by multiplying the 1 minus task similarity with the maximum number of prompts per task. We evaluated our approach on 3 datasets, namely CUB200, CIFAR100, and ImageNetR. Here are the results for the CIFAR100 and CUB200 datasets. As can be seen, our model outperforms existing approaches by a substantial margin while requiring fewer parameters. This makes our approach a step closer to the upper bound of jointly trained models. Additionally, our approach requires significantly less compute in comparison to existing approaches. So in conclusion, we proposed a convolutional prompting approach for continual learning, effectively utilizing task-shared concepts while keeping the parameter count low. With the use of task similarity to determine how many new convolutional kernels to be introduced further help reduce the number of parameters without losing on the performance. Through extensive experimentation, we have shown that our approach can outperform existing state-of-the-art while requiring lesser parameters. Thank you.